How's it going, you guys? In this video, I'm going to be talking about parametric equations. So essentially, what these represent are kind of how motion works. So if I were to have a ball, and I take this ball, and I throw it, I give it some vector. So remember, with vectors, they have a direction, they have a direction angle, and they also have some sort of magnitude or some sort of strength. But when I throw this ball, when it releases my hand, it follows this path until it hits whatever it's hitting over there. All right, so this path can be modeled by some parametric equations is what they are called. Because like to get to any point in this ball's flight path, I have an x and a y coordinate. When I throw this ball, it isn't everywhere all the time. Say this is after 1 second, say this is after like 2 seconds, say this is after like 3 seconds. They all have different xy coordinates. So the way we represent this as how it is changing over time is with time in our equations. So I'm just making something up. Alright, so those would be like what you would see for parametric equations. So notice we have an x direction. So x is our horizontal direction. So that is representing how far it is going in the x direction. So if I want to know how far it was in the x direction after 1 second, t represents time. So I plug in 1 for t. If I want to know how far it went in the y direction after 1 second, this is my equation for y. So I could plug in 1 for t here, and there should also be another t there. Doesn't matter. You're not going to have to like know those formulas. I could also plug in 1 for t there. But this is what parametric equations are good for. Before, you guys were graphing these things, and you would say that this would be a parabola, right? So really big parabola. It's really upside down, really big parabola. But parametric equations allow us to show what direction things are going in. So if I were to graph this thing, I could actually give it arrows, and I could tell what direction this thing is moving, this object is moving. So this is what parametric equations are good for. First thing I'm going to look at with you guys, may or may not have this, I don't know, but this is what I'm going to do with you guys. This is the worksheet that we do in class sometimes. So given the parametric equations, we're given x equals 3t plus 2. And just so you know, the t in this case is called our parameter. It's what our motion is based on. So kind of time is how as time changes, the object moves. And once later on, you will see where theta is our parameter. And as the angle changes is how things move. So first, to figure out how far we are going in the x direction, notice it has a time column here. So it has a bunch of t's. So if you want to figure out where it is in the t or in the x direction, we can plug in -3 to t. So 3 times -3 is -9, plus 2 is -7, and so on and so forth. Same thing with the y. We can do y equals -3 plus 3, which would be +6, and so on and so forth. I'm going to go ahead and fill this out real quick. Boom. There's our equation, or our values. Wow, I really cannot talk today. I'm sorry. I'm trying real hard. So these are essentially coordinates. This is the coordinate -7, 6, so I have -7, 6 right there. And then I have -4, 5, so -4, 5 right there. And then I have the next coordinate, the next coordinate, the next coordinate, the next coordinate, and the last one's off my page. So in graphing those coordinates, again, what I'm saying is this is telling us direction. So I know since time, the earliest time that I have is -3 seconds, so it's kind of like I'm looking backwards in time a little bit. So I am starting right here, and this particle is moving this direction. So the other thing I want to see when you graph is give me arrows on your shape so that I know what direction our particle is moving. It's going down and to the right. That is how our particle is moving. All right, write a function to represent the parametric equations. This is essentially just doing linear function. This is a line. So we can do y equals mx plus b, y equals, also, even easier, we can do y minus y1 equals our slope times x minus x1. So we know our slope. It looks like the slope is down 1 over 3, so our m is -1 over 3. a point. It doesn't matter which point you use, so I'm just going to use 11, 0. So we have y minus 0 equals negative 1/3 times x minus x1, which is 11. There is your equation. That's it. It's a line. It's not really anything super fancy or dancy about it. It's a line. The next part, right, the corresponding rectangular equation. All this means by rectangular equation is x and y coordinates, eliminating the parameter. So this eliminating the parameter, that's where in the beginning I said the parameter is t. So if I take both of those equations, x equals 3t plus 2 and y equals negative t plus 3, I know that t is represented by time in both of these equations. So if I know they are both time, what I could do is if I solve this equation for t, so if I have x minus 2 divided by 3 equals t, and I know t is x minus 2 divided by 3, if I take that x minus 2 divided by 3 and substitute it for t in my y equals equation, then I would have y equals negative x minus 2 over 3 plus 3. And I've essentially eliminated the parameter. I'm going to go ahead and simplify these numbers just a little bit to make them a little bit prettier. So if I distribute the negative to both of those, and I'm dividing by 3, so I would have, I'm going to go up here, y equals negative x over 3 plus 2/3 plus 3. And then 3 plus 2/3 is 11/3, so y equals negative x over 3 plus 11/3, which is exactly the same equation as this, where the negative 1/3 was actually distributed throughout. So eliminating the parameter is actually giving the function to represent the line. Sorry, wow, really can't talk today. So now moving forward, what is the x-intercept of the graph? So remember, an x-intercept is when our y equals 0. It looks like the x-intercept, we can't see it on our graph, it's somewhere over here, but we know when the y is 0 is at the point 11, 0 when time is 3. So it says, what is the x-intercept? It is 11, 0. For what value of t does it cross the x-axis is when t equals 2, 3. So this last part is going to require a little bit more work. It says, what is the y-intercept of the graph? Well, that's when x is 0. So I don't have, on my table, I don't have anywhere where my x is 0. Somewhere between those two, but I don't have it exactly on the table. So remember, you can solve for it too. If you have a y-intercept, again, it's where x is 0. So if you take your equation and you put in for 0 for x, we have y equals negative 0 over 3 plus 11/3. So hey-oh, our y-intercept then is 11/3. So I have 0, 11/3. And if I don't know what value of t it crosses the y-axis, I also have equations that are in terms of t. So if I know I'm on the y-axis, my x is 0. So if I use this equation and make x 0, I have 0 equals 3t plus 2. So if I subtract the 2, equals 3t divided by the 3, so time is negative 2/3 seconds. So that's my time, that's my y-intercept. Beautiful. That's essentially all there is to parametric equations. It's a little bit variated from there. So another one you could see is something like this, where I have my parametric equations, x equals 2 cosine, y equals 6 sine. It uses these charts to help you figure out what the graph is going to look at. So I'm going to take a second. Again, all I'm doing to figure out my x value, I plug in theta for my x equation. So it'll be x equals 2 cosine times 0, or cosine of 0 degrees, not times 0 degrees. What are you talking about? So I'm going to go ahead and fill out my x and y tables in both of these. There are our values. So then to graph these things, I'm going to go ahead and graph them as well. All right, so I know that's kind of hard to see, but there's our points. Let me zoom in a little bit. And if you kind of imagine in your head what shape those make, it looks like those make an ellipse. And if I'm starting at the point 2, 0, that's my very first point, and then it's going around this direction. So I'm just drawing it in the same direction as my particle. So again, show me the direction with some arrows. Beautiful arrows, so pretty. Pretty like bows. Oh yes, I like bows. Right, so there's our arrows, our parametric equations. They're going around this direction because that follows the angle, so it continuously rotates about that ellipse. So now to write a function that represents this graph, to write a function of an ellipse. It looks like the center is at 0, 0, so center at 0, 0. It looks like my A direction I have 2, my B direction I have 6. So I have the equation x squared over 4 plus y squared over 36 equals 1. There's our equation of our ellipse. Now let's see if we get the same equation again by eliminating our parameter. So now our two equations that we have, I'll write them down again on here, is x equals 2 cosine and y equals 6 sine theta. So now our parameter is theta in this case, and I need to get rid of it. Yeah, we could use inverse trig functions, but the easiest thing to do is remember back to chapter 5 for us. This is why we teach you things so that you can use them later on. We have the identity of sine squared plus cosine squared equals 1, such that they relate in the same identity. If I solve this equation for cosine, that would mean x over 2 equals cosine theta, and I solve this one for sine, which would be y over 6 is sine theta, then I can substitute these into my identity, because I essentially have y over 6 squared plus cosine is x over 2, so x over 2 squared equals 1. So I have y squared over 36 plus x squared over 4 equals 1. Hey-o, same exact equation. I mean, I just wrote it in a little bit different order, but it's the same thing. All right, what is the x-intercept of the graph? So the x-intercept is when y is 0. If we look at our tables, we have y is 0 right here when theta is 0 degrees. I also have y is 0 when it's 180. And I also have when I make a full circle of 360 degrees. So my x-intercepts are 2, 0 and negative 2, 0. And they happen when the theta is 0 degrees, 180 degrees, and again when it is 360 degrees, as it should. Whereas the y-intercept, so it's when the x is going to be 0. So the x is 0 at 90 degrees, the x is also 0 at 270 degrees. So I have 0, 6, 0, negative 6, so 0, 6, 0, negative 6. And I also have that happening when theta is 90 degrees or 270 degrees. Same. All right. Next thing I'm going to look at with you guys is just eliminating the parameter. So essentially getting rid of our t or our theta, the thing that is not x or y. So in this equation, it looks like to me it would be easiest if you just get x by itself. So you do x plus 1 over 3 equals t. And then you take this and plug it into t in that equation. So you have y equals 2 times x plus 1 over 3 plus 1. If you distribute the 2, this is y equals 2 thirds x plus 2 thirds plus 1. So that will be 5 thirds. So y equals 2 thirds x plus 5 over 3. Happy day. All right, same sort of idea here, but it looks like to get the t by itself, what I need to do is take the cube root. You can't really see that very well. Let me zoom in, zoom in, zoom in, zoom in, zoom in. Look at how big my hand is. It's okay, Cora. It's okay. That's what she sounds like when she's upset. She's getting up off the couch now. She's going to come fight me. Come fight me. That's what I thought. All right, but to get to t by itself, you can take the cube root on both sides. So we have t equals the cube root of x. So if I plug that into my y equals, I have y equals the cube root of x squared over 2. That's cool like that. All right, moving on a little bit. Here we have our parameter is theta. And I always think about, I look at these things and see how they relate. T, it's easy because the t equals each other, so you can just use that to your advantage and solve one of the equations for t. Here, especially since they're trig functions, I need to think about how they relate. So what I do is I know that secant is equal to 1 over cosine. So if I know that secant is x and cosine is y, then I have x equals 1 over y. And then to solve this thing for y, so that it'd be easier to graph if we wanted to, I can multiply by y on both sides. So I have xy equals 1, divide both sides by x, so I have y equals 1 over x. Hey-o, I've eliminated the parameter. All right, moving on. Doing good. Oh, yeah! This one's kind of tricky, but you just, again, remember those identities we taught you. That's why, again, we teach you things so that you can use them. Imagine that. All right. So I have tangent squared plus secant squared, or sorry, tangent squared plus 1 is secant squared. I use that one because I see tangent squared and secant squared in my parametric equation. Tangent squared is x, secant squared is y. Wow, that was easy, especially since you know your identity. All right, moving on. Last one I'm going to look at. So this is the same sort of idea where we need to use the identity of cosine squared plus sine squared equals 1. And if I solve my first equation for x, or sorry, for cosine, I would have cosine theta is x minus 4 over 2. If I solve the second one for sine, I need to add the 1, so that's just y plus 1. So when I substitute them into my equation, I have x minus 4 over 2 squared, because that's squared. And then I have y plus 1 squared equals 1. So I have x minus 4 squared over 4 plus y plus 1 squared over equals 1. And this would be an ellipse because essentially this is like it's over 1, so I have in the x direction I go 2, in the y direction I go 1, centered at 4, 1. 4, negative 1, 4, negative 1. Alright, as always, hopefully this video was helpful for you guys. Sorry that I was failing my words, but it's okay. There's like a very poorly drawn monkey as well to help you feel a little bit better about it. Alright, come talk to us. Come ask us questions. We're here for you guys. We love you guys.